the preparation of amines. Amines, remember, the organic compounds where we have the functional group N that can then be substituted coming from ammonia. And then in that way, depending on how many of the hydrogens had been substituted, we will say we have a primary amine, secondary, and a tertiary amine. Now, here let's have a brief discussion of the preparation of the amines. Many a time when they are prepared, we are going to make use of reduction. And you will remember in the organic, when we refer to reduction, addition of hydrogen. Now the first one there, they say we can prepare amines by reduction of nitriles. Nitriles, whenever we have the CN group, that we usually know as our cyano group. So when this is present in the organic, we refer to it as a nitrile group. And when hydrogens are added here, you are going to have CH2, and on the N, also H is added, NH2, and that is how you are going to have your amine then. So we can start here with any type of nitrile. Say, for example, we have the propyl nitrile, or actually here it's going to be a buta, because it's 1, 2, 3, 4. Now you remember we have to count that carbon in the nitrile as well. If you have that, and you now want to make this one an amine, you have to add hydrogens here. So you have to reduce. Reducing agent need to be the very strong reducing agent. So lithium aluminium hydride, and of course you will treat it with water. So first with the lithium aluminium hydride, then with the water, and we have here then our amine. And the amine is going to be a butyl amine because of the 4 carbons, and then the NH2. So reduction of nitriles is then one way to prepare the amine. Included here, we have the preparation of the nitrile itself. Now nitriles are very easily prepared by starting with an alkyl halide, and then just substitute that bromo group there with a CN group. You can take sodium cyanide, potassium cyanide, any salt containing the cyanide group, and then that cyanide can replace the Br, and in that way we have our nitrile CH3CN, which we then reduce, strong reducing agent, and we have our amine produced. Also another reduction process where we have an amide. Now amide is whenever you have the N, and onto the N you have a carbonyl group, the C double bond O. Now if we have the amide and we can reduce it, add H's, remove the O. Typical what we have when we have reduction in the organic chemistry, removal of oxygen and addition of hydrogen, and again you make use of the very strong reducing agent. Can you see the similarities there? Lithium aluminium hydride with water, lithium aluminium hydride with water, but two different starting materials. Now there you have the nitrile you start with, and here you have the amide you start with, and eventually you have your amine. Remember, to prepare the amide, the best way is, if you have a carboxylic acid, we will not directly let the carboxylic acid react with ammonia, because that will give you the ammonium salt. We prefer to go the way you see here. We start with our carboxylic acid, and then we treat it with thionyl chloride. In this way, we are going to prepare our acid chloride. So you actually have that Cl replacing the OH. So you have your acid chloride, and once we have the acid chloride, we can let it react with ammonia, and then we can see the H and the Cl will combine to give us HCl, and we have our amide prepared. And the amide you can then reduce with the lithium aluminium hydride, water, and you have your amine. So the oxygen is gone, you have hydrogens there, and you have your amine. So to reduction, another reduction process is when we have nitro compounds. We did this one before. You will remember when we did the benzene chemistry, we said that when you want to prepare aniline, you can first prepare your nitrobenzene. Let's have a quick look at that. If you have your benzene and we treat it with nitric acid, sulfuric acid, we end with our nitrobenzene. Now, if we reduce that nitrobenzene, we use iron in acid medium, or you will remember we can also use tin. We can use tin chloride. We can even use zinc and then treat it afterwards there with a basic solution. And when we do that, you have reduction of that nitro group. So oxygen's gone, you have hydrogen instead. And that is our amine now. So every time, it's interesting to see, every time we prepare our amine, we make use of reduction reactions. We can even use, with the nitro group, we can use hydrogen in the presence of the platinum catalyst, the process that we know very well for reduction. And you can also, in that way, prepare your amine. It's also useful to take note here, if we have another group present, like in this compound, this benzaldehyde here, we can now reduce the aldehyde group, and we can reduce our nitro group. So in a case like this, if you do not want that one to be reduced, then it's better to make use of the tin chloride, because the tin chloride is a very mild reducing agent. It will just reduce your nitro. The aldehyde will be remaining the way it had been before. And then you have your NO2 change to NH2. Substitution of alkyl halides is another method by which we can prepare our amines. What happened here? You have your CH3Br. When it's reacting with ammonia, we have one of the H's substituted by the methyl group there. But now you have this in the mixture together with more of that bromomethane group that you have there. So you can have further reaction between that methylamine of yours with a CH3, and you can have another hydrogen substituted, so that you end here with dimethylamine. Or, because this is now in the container with that, you can have another replacement, and you have your trimethyl. It can even happen that you have a fourth one. And then, of course, you are going to have the ammonium ion formed there. So, if in the mixture then, in the end, we have methylamine as product, we have dimethylamine as product, we have trimethylamine as product, and tetramethyl ammonium bromide as product. So in the mixture we are going to have lots of different things, and now it will be difficult for us to separate them again. That is why this method of preparation is not the preferred method to do the preparation of the amines. But we still take note of it. Then we can make use of azide. Even in the case of the azide, it's going to be a reduction process. Azide is whenever you have the N3 minus particle present. Now, if I have something, let's take the example you have there. If we have this benzyl bromide group, we can now let it react with any azide. It can be a sodium azide, and the azide is going to substitute that bromo group so that we have CH2N3. So now you have your benzyl azide, and the only thing we have to do here in order to have an amine is to add H's. So that's what we are going to do. We take that azide, and from the azide we reduce with the lithium aluminium hydride, and you are going to have your amine. Amine formed there because of the H's that is added. One other method by which we can do the preparation, if we have reductive amination of aldehydes and ketones. Important here, if you have your aldehyde or ketone and it reacts, you can have it reacting with ammonia, but you need to have this reducing conditions there. It could have been a sodium boron hydride as well, but hydrogen nickel catalyst also good. So any reducing agent then present there will give us the amine. Now here you have your primary amine reacting with your aldehyde ketone. Now usually if that was not present there, say for example you have this ketone and it reacts with a primary amine like methylamine, we would have expected to have H2O out and your product then look like this. You see all of that is still there. Where you have the O, it is now with the H2, and that NCH3 that is remaining, that is what we have on our carbon chain. So this, you will remember, is what we refer to as amines. And here, this is not what they show you. You have an amine formed still. The reason for that, that reducing agent that is present. So the moment you have the reducing agent, it changes the product that we find. So you no longer have the amine. If you have the reducing agent, you are going to have that amine reduced, and then you have an amine. So you will have H added there together with the CH3. You see that reducing agent will now reduce our amine so that we do not have it formed anymore. So the reductive, that reducing agent, is going to be important. So the moment it is there, if it's not there, then you know you are going to have the reactions, the nucleophilic additions that we had before. But when that reducing agent is present, it's changing the product, and you are going to end here with an amine. There you have your secondary amine reacting that usually will give us an N-amine. That's not what you have here. You are going to have the amine again, tertiary amine, because of that reducing agent that is present again. And then two very important preparation methods for our amines is the Hofmann rearrangement and the Curtius rearrangement reaction. The processes are very similar that we have here, but we start with two different starting materials. With Hofmann rearrangement, we start with amide. With the Curtius rearrangement, you will always see an azide. And then what we treat them with is also a different type of mixture. If I start with the amide and I treat it with Br2, bromine, in the basic solution, the sodium hydroxide and water, I have that carbonyl group. It's completely removed. If you compare what you see here with what you see there, you will see the difference is that you don't have that carbonyl. The CO is gone now. It's given off as carbon dioxide. So you only have now the NH2 where you had that C double bond O before. So our original chain here, it had 1, 2, 3, 4 carbons in the straight chain. Here you have only now 1, 2, 3. One of the carbons had been lost during the reaction there. And the same thing is happening with the Curtius rearrangement. So Curtius, you start with an azide. Now if you do not have an azide, like we did with the previous one, you will remember, it is important to have your acid chloride, then let it react with the azide and you have your azide. And now if I have azide, you can just treat it with water in the presence of heat. And again, you lose that C double bond O. So you still have the CH3, you still have the CH2, and then immediately you have your N with the hydrogens added. You have the reduction. But that CO, it's no longer there. So here we had a propanohol azide. But our final product is an ethylamine. One of our carbons is no longer there. So with Hofmann rearrangement, you are going to lose a carbon in your compound, and with Curtius rearrangement, the same, but they differ. Because Hofmann start with an amide, Curtius start with azide. Or if you have an acid chloride, doesn't matter, you'll have to change it to azide because you need the azide to do the Curtius rearrangement. And then when you have the azide, you can treat it with water and you have your amine. Now that is the different ways in which amines can then be prepared. We have just a few reactions of the amines that we need to have a look at. Alkylation, we actually already did, where you have your amine and it's reacting with an alkyl halide. These CH3s there substitute the H's on the N, and you have different types of amines formed. Now that's alkylation. In other words, extra alkyl groups are added onto your amine. Now that's what this alkylation reaction is referring to. Or we can have acylation. Now very similar to the alkylation process. The only difference is now you are going to have the acyl group present. So you are going to have that C double bond O group, and you have your amide formed in that way. Take note of this last one. That is a very important one to us. It's a name reaction again. Hofmann elimination. Remember the other reaction we had was Hofmann rearrangement. There's a difference. Hofmann rearrangement is used to prepare amines. Hofmann elimination is a reaction that the amines can undergo. And elimination, we know, always give us an unsaturated product. Have a look at the product there. It's an alkene formed, exactly what we would have expected. Elimination reaction giving us an alkene. Have a quick look at it. There you have the amine. We treat it with excess methyl iodide there. You take excess of that, and what happens is our CH3s, they substitute the H's, and because you add excess, you are going to have all your H's substituted and even more, so that you have your ammonium ion formed there. And once you have that, it is treated with silver oxide and heat, and that is removed, and you have your alkene. Now, interesting, if we take the elimination reaction there, Say for example we have this alkyl halide. The 2-chloro-pentane, and we do the elimination reaction there, treating it with a potassium hydroxide in alcohol. And we look at our product. Me and you would say here, our major product will be when we have the double bond in this position. And the rule we make use of is our Zaitsev rule. Now look at what happened in this case. It is not the same. You have your double bond onto onto the starting point there of your alkene. So what we have to say to ourselves, whenever we have Hofmann elimination, it will take place anti-Zaitsev. So your product is anti-Zaitsev and not according to the rule. If you have to write this Hofmann elimination reaction, you need not to show me that intermediate. You can directly go from your amine, say I treat it there with the excess of the methyl iodide, and then with a silver oxide and heat, and you have your alkene. Now that is the very important reaction that we have for the amines. Now at this stage we are not going to include any further reactions for the amines. That will be done in a later course of organic chemistry. Thank you.